So hello everybody, my name is Pavol Loffay, and in this presentation I will talk about distributed tracing for microprofile runtimes. So on today's agenda there is an introduction to distributed tracing concepts and especially to distributed context propagation as it is the foundation for distributed tracing. Then I will talk about MicroProfile-OpenTracing features and demonstrate that in a microservice-based application developed in Runtimes and monitored by Jaeger, which is a project which is distributed tracing tool hosted under the Cloud Native Computing Foundation. So before we start, I would like to introduce you to myself. I'm a software engineer at Red Hat. I've been working on distributed tracing and observability for the last 3 years. And at the moment, I'm a committer and maintainer on Jaeger and OpenTracing projects. And I'm also working on the MicroProfile-OpenTracing. So on the slides, there is my GitHub and Twitter handle in case you want to follow me. So when I started preparing for this presentation, I deployed a couple of microservices to OpenShift. And to verify my deployment, I created a request to the cluster, and it's obviously failed. And it's obvious that it's something related to DNS, but I wasn't sure whether it's configuration on my machine or it's configuration in an OpenShift cluster, or maybe just a random DNS failure. And my point here is that DNS is a distributed system, and to really debug this kind of transaction, we would have to have access to all of the debug information from all of the nodes involved in the transactions, which we obviously don't have. So when talking about large applications, on this slide you can see a cloud-native application which maybe consists of hundreds or thousands of nodes. And when the request comes to this application, it's usually served by maybe dozens or hundreds of services. My question is, how do we monitor such a system? So traditionally, we used to deploy logging and metric systems, which basically allows us to tell the story about our application and help us to understand what is happening. Both of these systems work well on they work on an event-based model, let's say. So log is an event, is a time-stamped event which contains a string data, which can be like a stack trace, an error message, or any meaningful string, which can be used later on to analyze what happened. From the instrumentation side, there is very good support. We have APIs like SLI4j, Log4j, and to collect and visualize logs, there are tools like Elasticsearch, Logstash, Fluentd, or Splunk. Metrics are a little bit different to logs. They do not provide any like debug information like string which you can read. They just provide a single numerical values like like counters, timers, and histograms. When you compare it to logs, metrics provide us like more real-time feedback about the system. And if you want to instrument with metrics, there is also very good support in the industry. We have, for example, microprofile metrics, micrometers, or Wizard. And to collect and visualize metrics, there is also a lot of good tools like Prometheus, Grafana, and StatsD. And what is the ultimate goal of this system? It's obviously to tell you the story, what is happening in your system. And can these tools work well in highly distributed systems like we saw on the previous slide? Well, probably to some degree, but they may fail you to tell the story when the request goes through multiple endpoints and multiple nodes. And here is where distributed tracing can help you to understand distributed transactions. So before we deep dive into like MicroProfile-OpenTracing specification and features of tracing system, I would like to quickly demonstrate how actually tracing can be implemented. So on this slide, you can see 5 nodes. There is node A, B, C, D, and E. And there is a request coming, for example, from the web browser or from the client. So what happens? Tracing integration or tracing client, when the request arrives to the first service, it creates a context. And this context contains the unique ID, which we call usually trace ID. And the trace ID is unique for the lifetime of the request. So if a service A calls downstream service, like in this case B and E, the context is propagated to those services. In a B, the same thing happens. The context is propagated from inbound to outbound request. And then later on, after the invocation, tracing system can correlate these events based on this trace ID and show you like the call graph would happen. And this is usually presented as a Gantt chart, which is shown on the right side of the slide. And what is nice about this is that you can really see like where the time was spent. So by looking at this, we can see that the A service had to wait for the B and basically for all of the services to finish. And afterwards, the response was sent to the client. We can also guess that, for example, the C and D could have been in parallel. So for example, the invocation in B could be shorter. So what I described on the previous slide was really like distributed context propagation. It wasn't really tracing. And my point here is that the context propagation is really foundation to implement a distributed tracing system. If you have that in place, we can do things like distributed transaction monitoring, root cause analysis, performance latency optimization, and also service dependency analysis. So you may wonder why I didn't mention distributed tracing on one of the first slides when I was talking about metrics and logs. And that's because distributed tracing is still not as mainstream as metrics and logs. And that's because the context propagation. So it's a little bit harder to do tracing than metrics and logs because you have to propagate this context. And actually the problem is not to propagate it, like to put something into the headers or just extract it from the headers. The problem is how we propagate the context inside the service. So on this slide you can see a service, and what service has to do in order to propagate the context. It has to like extract the context from the headers, store it somewhere, and on the client side get it, put it into the headers, and that the context is sent out, right? So in Java we are kind of lucky because we have the thread locals, so we can store the context in thread locals. But the problem is that nowadays you write quite complicated code using a lot of thread pools, queues, and futures, and thread locals just do not work well with these design patterns. It's not something impossible to do to propagate the context through different threads. It just requires more work. So this was really the overview, like how tracing works and what is usually the problem associated with it. And on the next slide, I would like to focus on the MicroProfile-OpenTracing. So OpenTracing is actually very similar to MicroProfile. It's also specification and send of APIs, but with a single goal. Its goal is to describe distributed transactions. And what we did in MicroProfile, we took this specification and defined behavior and set of additional APIs to make it easier to use in Java EE applications. So as I mentioned that in tracing, it's important to see like the invocation between services and basically the only like server-side framework or the technology which is used inside MicroProfile which can propagate something between services is JAX-RS. So we decided that JAX-RS will be automatically traced. So if you include the MicroProfile-OpenTracing spec, all of your JAX-RS endpoints are automatically traced. The client is a little bit more complicated. I will talk about this later in the demo. So we have the automatic tracing for JAX-RS framework. Then the other part of the specification is so-called explicit tracing. And this allows you to use OpenTracing API directly inside your code. So you can, on this slide, there is this tracer, which is OpenTracing interface. You can use it directly to create tracing events, for example, inside your business logic, or you can use it to add additional data, which can be then queried in the tracing backend. We also defined the trace annotation that can be used to enable tracing for CDI beans and also to disable tracing for example, for JAX-RS endpoint or for the whole class. The next part is configuration. So we are leveraging the microprofile config, and at the moment there are only two configuration properties. The first one is to configure the server operation name of a span. So by default, the operation name looks like HTTP method, the package name, class name, and the method which is in the code. But you can change that to, for example, to the value which is used inside the path annotation. The second property is used to disable tracing for specific URLs. So as I said, the JAX-RS is automatically traced, but sometimes you would like to disable tracing for specific endpoints. And this is great because you can use just configuration property to do that. Also, what happens, a lot of people ask me like, where is the tracer configuration, right? And tracer is not defined by OpenTracing specification nor the microprofile, so it's something which is vendor specific, so it's not exposed by any of these specifications. So really then for example, in Trontail we have Jaeger configuration, but in OpenLiberty exposes a Zipkin configuration. And even like if OpenLiberty will integrate, if the OpenLiberty integrates with Jaeger, then they may decide like expose different set of properties. So going to the demo, it's a simple microservice-based application. There are two services, the front end and the back end. The back end defines three endpoints. The first is fail, which returns 500. Then the OK, which returns 200. And the random, which returns, like based on the probability, 500 or 200. The the code is available on the GitLab. You can see the URL. There is also tracing branch and set of tags which like guides you through different steps, which I will show you in a minute. So I will jump to the IDE. So we can see there are two services, the front end and the back end. The front-end service, there is only one handler. It's front-end handler with only one method. Accepts mode parameter with default value OK. And inside we call some CDI bean, we do some work, and then we call the backend service, which is also like CDI bean, which then uses the client to call the backend service. And this response is propagated back to the like browser or the client. The backend REST API is this one. We have three methods, and then the backend handler implements the API. So there is a failure, OK, and random. Okay, so I will start the backend and the frontend. I will also start Jaeger server. I'm starting it from the source, but you can also use the Docker or just download the binary and run it from the binary. So Trontail is ready. So I will just invoke the OK, provide the query parameter OK, and we can see a response from the server. I can do it like two times, 3 times. So in the Jaeger UI, we can see there are some traces. So this is Jaeger UI, and the first thing what you have to do is to choose the service name, which is here, and we can see there is a backend and the front end. So you can select that and see traces which are going through these services. So in our case, I will choose the front end because that's the first one in the invocation. And we can see here the traces. The interesting part here is that, for example, this one took 437 milliseconds, and the second one 35 milliseconds. And that's because this one was the first request to those services, and they had to do some initialization and had to load classes, so it took like significantly longer. So let's choose, for example, this one. And on this screen, you can see the whole invocation. Each line represents the so-called like invocation unit, which we call span. So we can click on the first one, and by looking at the data from the trace, we can see that it was reported by JAX-RS, and it represents a server invocation of this endpoint. This is actually front-end service, so we can see that here. So the front-end service invocation for this endpoint reported this span. The next span, we see the operation name is get. And by looking at the tags, you can see that it was a client invocation for this URL. So we can see this URL corresponds to the backend service. So the front end was calling backend. And the last span is from the backend service. You can see here the backend service, the class name and the method name. And what is interesting on this trace is that we see that something happened here, but we do not see what. So we can go back to the code, to the front-end handler, I think it's here, and just investigate that, right? So we can see it's pretty simple. It's incrementing a call count, then it's doing some work, and then it's calling the backend service, right? So maybe this do work is on a critical path, and it's doing a lot of work, and it would be nice to get some timing information for the invocation, right? So we can go to the bean and simply add traced annotation. And if we restart the application, we should see a separate span modeling this invocation of the bean. By adding on the class, all the methods will be traced. In this case, there is only one method, but if it had more, all the methods would be traced. So turntail is up. I can do request to the same URL. Yeah, and here we can also see the same pattern. The first request, it took like 300 milliseconds, and the second one only 36. Let's choose this one. And the first difference is that the number of spans increased, and there is a span for the do work. And in this case, like it's doing almost nothing, so there is no really like the invocation is very short, so it's obviously not on the critical path. I don't want to investigate why the invocation took like 36 milliseconds, and it could take only like maybe 6 or 7 because this took 4. It's maybe because the fault tolerance, which is used on the backend service, took some time, or maybe the CDI bean creation took some time. Maybe something like that is causing the delay here in between. The next thing I would like to show you is on the backend service, there is this random handler, And based on the probability, it sometimes returns 200 and sometimes 500. So if the probability is less than 50%, it will return OK, and it's more than server error. So I can try to call it. Whoops, sorry. We can see the response changed to good. It's a different endpoint. We see it's always the same, right? So probably it works fine. But sometimes it takes longer. Sometimes it's shorter. So we can go back to Jaeger and see what's happening. And we see that sometimes there are 4 spans, which is the same as previous, and sometimes there are 10 spans. So why is that? If I look at the 10 span, I can see there are way more invocations. So after do work, there is call to the backend. 1, 2, 3, 4 calls to the backend. And we can see there is also some delay between these calls. And this is because the fault tolerance. So why fault tolerance, right? So if I investigate this call, for example, the first one, I can see that it returned 500, right? So it's failed request. And what happens with MicroProfile REST client, if the 500 is returned from the server, it will throw exception. And then the fault tolerance will retry. What we can do also with tracing to understand why it was retried, we can in a backend handler there is this probability, right? So we can add the probability to the current active span and then see it in the backend in the tracing system. So I can use tracer and add it as a tag. You have to provide the key. You can call it probability. And we have to restart the backend service. Okay. So we see the same response as before. So for example, let's choose this. This is 2 minutes ago, so this one. Now I can see the probability is added to the server span representing the backend invocation. And we see that it was like 67%, so the error was returned. We can also have a look at the last backend invocation, and we see the probability was only 11%, so the OK was returned and the whole transaction succeeded. So by using OpenTracing API, you can enrich the tracing information with your business data, basically. The last part of the demo, I would like to show you how you can propagate additional data between services without changing any public APIs. So from the imagine browser is sending the user agent header to the front end, and then the front end is calling the backend service, right? But you lose the user agent because the front end uses different client, right? And it will use the different user agent. And imagine you would like to use the original user agent in the backend service, for example, to do canary deployment, like to distinguish, for example, iOS users from or Safari users from the Firefox or something like that. So in order to do that, you would have to change the front-end API to propagated header back to the backend, or just change the front-end, like also, yeah, the API and also the internal APIs, because you have to propagate more data, right? But we are using OpenTracing, so there is this feature called baggage propagation. So in a front-end handler, this is the first service, right? So I have to somehow get the user agent header from the browser. So I have to inject it here. And then add it to the current active span. Set baggage, so we can call it like agent, short name. Then in the backend service, for example, in the OK handler, I can print it out. You just get the baggage, use the same key, and print it out, right? I have to restart both services. Okay. So I will invoke the OK endpoint with using user agent Eclipse. So I'm calling the front-end service, and the user agent, whoa, there was some error, but the user agent in the backend service, it's propagated and it's print out the standard output. We can also use the default one. And we can see this is the curl. This is the output from the backend service. What I can also do is to change the backend service, inject the user, the header param. Well, we have to. I could also inject here the header param and the user agent header parameter and print it out in the backend handler, and we will see that it would be the value would be the from the HTTP client used by the REST client from the front-end service, which is, I think, the Apache client. Okay, so this was for the demo, and the last part that I have here, it's something about future work. So in the next releases, we will support better integration with MicroProfile REST client, and also solve some problems with context propagation inside MicroProfile fault tolerance. Provide maybe new annotations to add metadata to the current active span. Maybe also probably something with CDI, so you don't have to use trace annotation to explicitly enable tracing there, but you could, for example, use microprofile config and define, for example, the package name, and all the beans in that package would be automatically traced. It's also important to mention that you can use any OpenTracing instrumentations with MicroProfile. So if you are using JDBC, Redis, or Kafka, you can use that existing instrumentation inside your MicroProfile runtime. Okay, that's everything what I have for today. Thank you. Do you have any questions? Yeah.
I think what could be one more comment on the question, what could be helpful is to inject the active span instead of the tracer. Or additionally allow that, and then you don't have to always go tracer dot get active span dot directly have this one. I think this would be pretty convenient.
Yeah. I think the before in the, not in MicroProfile, but there is Jaxer's instrumentation for OpenTracing Jaxer instrumentation. What we had there, you could inject wrapper for active span inside a handler parameter. Like you write the context and use the context, the annotation to inject. Other questions? Yeah.
Yeah. So for me, tracing is a very important part to analyze performance, especially in distributed applications. And I'm also working in that area. So I'm in Eclipse Trace Compass project, and we consume traces from different sources, and we provide trace analysis and trace visualizations.
Cool.
So I invite you to come maybe tomorrow to the talk, where we can talk about that. It has some interesting features like critical path analysis. Looking on, if you have this huge cluster you trace, you want to see what really contributes to the critical path. So that's yeah, and we also looked into to support Jaeger tracing in the tool. It's more in incubation situation, but it has a lot of overlap due to Jaeger UI.
Definitely, yeah. What kind of like model do you use, or Zipkin, or to model in the invocations?
We look at the traces, and then maybe we have a way to store like states which corresponds to spans in your Jaeger UI, and we have an efficient way to store that on disk and be query that information.
I think it looks interesting.
And right now it's an Eclipse RCP application, but in the future we planning and provide a web UI. So then it would be, yeah, maybe there are ways to collaborate or
yeah, definitely.
Yeah, benefits
yeah. This is everything, yeah, open source, so we can do something together.
The second thing, we're collaborating with the Trace Research Project in Montreal, and they are looking into analysis of distributed traces, and they use also Jaeger as a way. So there's some interesting things going on.
Cool. I'm looking forward to hear more. Okay, thank you. More questions? Okay, so thank you.